The first talk will be given by Oshri Halimi, joint work with Kimmel, and the title of the talk is Self-Functional Maps.
Okay. Hello, everyone. My name is Oshri, and as Shai said, I'm a student of Professor Kimmel from Technion. And in this presentation, I would like to introduce the idea of self-functional maps. Okay, so now it's better? So in this presentation, I would like to introduce the idea of self-functional maps. And I would like to motivate the discussion. Let's think about the following scenario. Let's imagine that we have a data set of human scans, okay? And we scan a new person, and we want to know if this person already appears in this data set or not. Okay, so still this person can appear in this data set in a different position than the scan's position. And we would like to provide a positive answer if the person appears in the data set, no matter in which position he was scanned. So we would like to have some signature which will be... Thank you. Okay, so we would like to have some signature which will be invariant to the type of transformation that are used to model the different pose articulations of the same shape. And here we come to self-functional maps. Self-functional maps are all about it because basically this is an algebraic representation, a matrix representation, as can be seen here, which is preserved between different poses of the same shape. As can be seen here, we can see the different poses of the same horse and the different poses of the same woman. And we can see that this signature is preserved between the different poses, but it is still distinguished. It is still unique between different shapes that doesn't relate to each other by this transformation. Okay, so effectively the problem of comparison between geometrical objects, between surfaces, is translated to the problem of comparing between algebraic representation, namely matrices. And we can define some distances between matrices. And okay, so this is how we can address the problem of comparing surfaces. And I would like to address more what type of geometrical information is actually encoded by the self-functional map. So here we can see the general pipeline. We can see a surface. Here is a horse. And the output of this pipeline is basically an image, a matrix. And we're doing it by the following procedure. We just take the surface, which is a particular case of a topological object. It is a particular case of a two-dimensional manifold. And we define two different metrics on the surface. And by this, we get two different metric spaces, two different Riemannian manifolds, denoted here by G and G tilde. The metrics are denoted by G and G tilde. And this tuple is the resulting Riemannian manifolds. And in each metric space, separately, we define the respective Laplace Beltrami operator. And we perform eigendecomposition, resulting in two different families of eigenfunctions, corresponding to each operator. And finally, we combine these functions by taking the mutual inner products, and we can see that the entries of the matrix are encoding the inner products. Okay, so this is a pipeline, and let's see this animation. We can see two different shapes, a horse and a centaur. And we can see alongside the animation for the self-functional map. And one can observe that between different frames, the self-functional map is more or less preserved in a very good approximation, but it is still distinguishable and still function as a signature between different shapes. Okay, so we can take a data set consisting of many shapes, and we can define distances between the matrices. And finally, we can take these surfaces and embed them in the Euclidean space. Each point here corresponds to a different surface, and we can observe the formation of clustering. Each cluster corresponds to a different shape, and within the cluster, each point corresponds to a different pose of the surface. And we can see, for example, a cluster that corresponds to the cats and a cluster for the horses. And okay, so self-functional map can be used for the task of surface classification. Okay, so just very briefly, let's introduce some metric spaces definition. Basically, if we have a surface, for a general surface, it's impossible to define a global parametrization, but still, locally, in every point on the surface, we can define a tangent space, a tangent plane, and in this tangent plane, we can define a local coordinate system. And the metric tensor, if we have some displacement vector from the original point and we want to measure the infinitesimal length associated with this vector, we can use the metric tensor G to measure the infinitesimal length. And finally, if we have some global trajectory on the surface, we can just integrate all the infinitesimal lengths and calculate the global length of each trajectory, and we calculate basically any distance on the surface using the metric tensor. Okay, so the previous one was the definition of the standard Euclidean metric, but there are many ways that one could define the metric tensor. For example, one very interesting choice might be the scale invariant metric. We get the scale invariant metric by scaling the standard metric by the Gaussian curvature. And intuitively, we can think that we don't measure the actual distance between points, but rather the distance normalized by the local radius of curvature. So 2 points that are very close to each other from the point of view of the standard metric can be appeared far apart from this point of view of the scale invariant metric if they are in a very curved region. So, for example, we can see here gamma 1 and gamma 2, and from the point of view of the standard metric, these trajectories have the same length, but from the point of view of the scale invariant metric, the first one has larger length. So, we have 2 different metrics, and basically, each metric has a very different way to measure distances on the surface, and we can combine these different perspectives to construct our signature, the cell function maps. So there are pairs of examples that for pairs of surfaces that can be considered isometric from the point of view of one metric, but still non-isometric from the point of view of the second metric. For example, if we take a sphere and we cut it in half and we construct a spherocylinder with very short, approaching zero, cylinder height, we can see that from the point of view of the Euclidean metric, nothing really happened. The distances were preserved, but from the point of view of the scale invariant metric, the change is dramatic. Since all the points on the equator that originally were separated by a finite length now are shrinked to a point due to the formation of a trajectory of zero length on the spherocylinder. And contrarily, we can see that all these surfaces that are, of course, non-isometric from the point of view of the standard metric are considered isometric from the point of view of the scale invariant metric. Basically, any composition of radius scale and axis elongation of the cylinder is resulting in isometric surface from the point of view of the scale invariant metric. Okay, so this animation is about the previous example. Okay, a very fundamental operator that one can define on surfaces is the Laplace-Beltrami operator, which is a generalization of the Laplacian operator from Euclidean spaces to curved domains. And the eigen decomposition of this operator generalizes the notion of Fourier basis and Fourier transform. And basically, we can represent any scalar function that is defined on the surface using a series of these functions. And one important property of the Laplace-Beltrami operator is that it is intrinsic, which means it can be expressed solely in terms of the metric, okay? And another property is that this operator is isometry invariant, means it is not changed between different isometries which are used to model different poses of the same shape. So this operator is preserved. Okay, so we can take a surface and we can calculate the eigenfunctions with respect to each Laplace-Beltrami operator. And in the first row, we see the eigenfunctions of the regular Laplace-Beltrami operator. And in the second, we can see the scale invariant eigenfunctions. And one very obvious thing that we could observe that is the fast transition of the scale invariant functions in curve domain. Here we zoom in this region, we can see that in curve domain, even though the effective distance is very small, we can observe a fast transition. While on flat domains, for example, see the number 5 eigenfunction, on flat domain, the phase is approximately constant, and only when we reach curve domain, the phases start to change. Okay, so we have two different families of eigenfunctions. And we can take a surface and practically convert it into an image. And this representation is very appealing since for graph structure and for discrete surfaces, which is basically a graph structure, the question of how to design an architecture that will take this structure as an input is an open question. But for images, we have standard deep learning schemes, such as CNN, etc. And we can just take this representation and process it using deep learning methods, existing deep learning methods. Okay. So now I would like to address the relation to the formalism of function maps. Okay, so function maps were introduced to answer a completely different problem, the problem of shape correspondence. Basically, if we have let's say two non-rigid objects that are related to each other by some pose transformation, we would like to draw matching between the points on the surfaces, for example, to map the elbow to the elbow, the finger to the finger, etc. So we could address this as a pointwise correspondence problem. But the pointwise formulation results in a very complex problem to solve, basically to quadratic assignment problem, okay? But introducing the paradigm shift of the function maps, which is about, now we don't ask the question how to map a point to a point, we ask the question if we have some function defined on the source domain and we want to map it to the target domain, how can we do it? And one can observe that this formalism encapsulates the previous formalism, because if we know how to map any function to any function, we can always construct some very local function on some point and map it to the target domain. And by this, as a byproduct, we get the pointwise correspondence, okay? But the second formalism has the advantage that it leads to a linear problem, basically to a system of linear equations. And okay, so it's preferred formalism. And we are doing so by introducing an object called functional maps, okay? The functional map is a matrix, and in this matrix, each entry corresponds to the following. We take a function, a basis function on the source shape, we map it to the target shape, and we project it on a basis function that is defined on the target shape. So we have all these entries. And we can see that this formalism generalizes the cell function map, because here we are talking about two metric spaces resulting from the surface. So the transformation is the identity. We can plug the identity instead of T. And instead of the bases, once we take the regular Laplace Beltrami eigenfunction or the scale invariant one. So we can see that now T is removed from this inner product. And we can see that the mutual inner product is encoded in the cell function map. Okay, so we have a pipeline. We have a pipeline to take a surface and to convert it into an image, as we discussed by the eigendecomposition separately in each metric space. And now we would like to define a distance between the images and to define actually distance between the surfaces. So a very basic distance that one can think of is the L1 distance between the matrices. Or we can define some more robust L1 distance that has the properties it is robust to permutation. But basically we can use many notions of distance. And we can take a data set and calculate all the interdistance between the shapes. And this results in a block diagonal matrix, which means that it leads to formation of clusters. And for example, here we take Faust, a data set of human scans, and we can see here clusters where each cluster corresponds to a different human identity, and within each cluster, the points correspond to different poses of each identity. And another example, we take, for example, synthetic human shapes, and it results in clustering. Or another example of real human shapes from a Shrek 14 dataset. And here is Tosca. Okay, so we have empirical evidence that self-function maps can be used for the task of object classification, but there are many open theoretical questions that can be asked. For example, if we start from two isometric surfaces, we know that the self-function map will be the same by construction, because Laplace-Beltrami operator is isometry invariant, and also the Gaussian curvature is isometry invariant. But can we ask the opposite question? Namely, if we know the two shapes have the same self-function map, can we deduce that these shapes are isometric? Okay, so we started to answer this question for planar curves. For planar curves, we show some theoretical results, and we relate the self-function map to the famous Cartan invariant signatures. And another interesting question that can be asked, can we reconstruct the surface out of the self-function map? Or can we define it with respect to different transformation rather than just pose articulation? Maybe this formalism is flexible and allows us to do it. Okay, so let me skip the proof slides. Let me just state the Cartan theorem. Cartan's theorem states the following. If two planar curves are related to each other by Euclidean transformation, namely by rotation and translation, it means that they share the same invariant signature which appears at the bottom. They have this same functional dependency between the derivative of the curvature and the curvature itself. And Cartan's theorem states that if we know that for two curves the signature is the same, they must relate to each other by Euclidean transformation. And we can prove, I will not delve into the details, but it can be proved that if we know for curves that the self-function map is the same, it implies that the Cartan's invariant signatures are the same, and this implies that the curves are related to each other by Euclidean transformation. And we try to generalize these results also to surfaces, but this is of course much more challenging since for surfaces we don't have global parametrization, but we work on it, and hopefully we'll have some results soon. Okay, so a different question that we can ask is, if we have different transformation, now we're not dealing with transformation that it is preserved by pose articulation, but let's say we have a data set of humans and we want to cluster not according to the identity, but according to the pose. We want to be completely agnostic to the identity. We just want to know that this person is raising his head, or I don't know, is being in some pose. We just want to extract this information and be agnostic to the identity. So, of course, we cannot doing it by intrinsic operators because they are invariant to the pose, but using extrinsic operators, we can do it, and there is Steklov-Wiegand problem, and we can use Steklov operator, and to use different pair of operator to achieve pose clustering. And here we can see the same Faust dataset. You can look at it once we cluster according to the self-function map where they are defined with Laplace-Beltrami operator, the regular and the scale invariant, and we get identity clustering. And once we defined it with Steklov extrinsic operator, and we can achieve, on the same dataset, we can achieve pose clustering. So this object is very flexible, and we would like to explore it with different pairs of operator. If someone has a, I don't know, suggestion to interesting operator, I would like to explore it. And thank you for listening. And if you have any questions.
Questions? Let me have one.
Okay.
So you started by introducing this scale invariant, but I wasn't sure where exactly it helped you in the solution. What happens if you're not using the scale invariant in your signature method? If
you're not using the scale invariant. Okay, very good question. The scale invariant metric was used As an example, because for the definition of the cell function map, as we said, we measure interaction between pair of operators. So we choose for the example of the isometry transformation, we choose a pair of operators which are isometry invariant. And the scale invariant metric is by construction isometry invariant because the Laplace Beltrami is isometry invariant, and also the curvature is isometry invariant. So we achieve an isometry invariant signature, and basically for different poses, it is preserved. But this structure, this interaction is rich enough to create off-diagonal patterns that can be used as a signature to distinguish between different shapes.
Any more questions? Okay, let's thank the speaker.